All right, now let's start on some examples. Example 1 says in this sketch, theta is in standard position. Remember, standard position, this is a throwback to 3, 2. Means your initial side's on the x-axis, and theta represents the count of radiuses to get to the terminal side. Pxy, this point P, is the point on the unit circle that corresponds to theta. Complete the table in terms of x and y. Okay, I gave you a rhyme on lesson 3-2. I said that sine is y. And it's not just y by itself. What is sine ratio? Y over r. Okay, on this problem, let's look. This point has a y value connected. What is its y value? Y. It's just y. So that stays there. But r, if you look, we can actually determine r by looking at the initial side. The initial side, this radius from this point to this point, we can mathematically calculate. What's the length of this radius? 1. So truthfully, sine would be, if it's y over r, it would be y over 1. And what is y divided by 1? Y. And that's why we say on a unit circle, sine is y. Cos, what would cos be? X over r. And once again, in this case, it's x divided by 1. Therefore, cosine on a unit circle could be said to be x. Sine is y, cos is x. Tangent is y over x. In this problem, we don't know y, we don't know x. Other than we could say x is negative because it's on the left side. It's going to be a negative value, but I'm just going to leave it like that. Okay, so today we're talking about the reciprocal functions. Reciprocal means you flip. So instead of, if sine is y over r, then that means cosecant is r over y, which in this case would become 1 over y. Make my y's look the same here. 1 over y. Okay, what about secant? That does not reduce, by the way. 1 over y would stay. It would be r divided by x. Perfect. And if it's r divided by x on this particular unit circle, it would be 1 divided by the x value, which again, the x value would be negative because we're on the left side. Finally, cotangent could be described as x over y. Very good. So that's just to give you a general overview of what the functions are, how they're calculated. Now, part B through part D, is that right? Let me check here. Part B through E is going to deal a little bit more in detail with all these functions. So to help us out, up at the top, we're going to have to do this kind of small. We're going to draw a graph for sine and cosine because it'll help us solve these. Remember sine, when we graph sine, let's see, sorry, x-axis, this is going to be for sine. Then we're going to go draw a graph for cosine. And then I'm going to draw a graph for tangent. And try to sneak those in. Tangents, I'm going to put the y-axis in the middle. Sine, do you remember, think about the unit circle. Does sine begin at its maximum, minimum, or midline? Midline. Sine begins at its midline, perfect. Put a dot at the origin. Now does sine, what does it look like? Does it look like parabolas, S-curves, waves? What does sine look like? Waves. Draw a wave that increases to its maximum, comes down, its minimum, and then just draw an arrow going this way and an arrow like this going that way. That is sine x. I will pick back up on cosine in a moment. Let's use this for sine. Sine, where in this wave does the graph break? Undefined means there's a break. Where does the sine wave break? Never. It never does. Let's do NA. It starts repeating at 2 pi. 2 pi would be its period, but it does not break. Okay, domain. How far to the left would this wave travel? Infinity. Negative infinity. How far to the right? Perfect. You could write it that way, or you could do XER. However you wanted to write that. We're talking about domain, that's the x values. You could say x is any real number. E means is any. Okay, now let's talk about the range. This means low to high. How low does the sine graph travel? Not negative infinity. -1. How high does a sine wave travel? 1. Okay, so the range is going to be -1 to 1. Now let's talk about cosine. Cosine was very, very similar to sine. What was the difference, though, in the cosine wave? It starts at its maximum. So if you start at the maximum here, we're going to draw another wave, and it's going to complete. Well, let me actually make it start going back down. It'll complete its period once again at 2 pi. You know, I didn't put 2 pi in on sines. Let me do that. Where right there, that would be 2 pi. All right, great. And what's the low point here on cosine's wave? Perfect. Okay, so same questions now. We're talking about cosine. This is y equals cosine x. When we examine this, tell me about the wave. Where do we have a break on this wave? Never. No breaks. Okay. How about the domain? How far left? How far right? It's all real. So it goes left forever. It travels right forever. You could write it whichever way you prefer. X is any real number, or you could say from negative infinity all the way to positive infinity, which includes all real numbers. Talk about the range. How low does this graph travel? How high? -1 to 1. Now finally, tangent. Does anybody remember what tangent looked like? It wasn't a wave. A whole bunch of S curves. They repeat over and over and over. They had asymptotes. Just do an asymptote to the left and to the right, and I'm only going to do this, and I'll do 3 waves in between. Those asymptotes occurred at pi over 2. So on the left, if you remember, the rule was the left asymptote we saw for was negative pi over 2. The right asymptote was positive pi over 2. So label that, and I'm going to do the actual graph in green. So it came up like an S curve, and it just repeats itself. So if you best you can, try to draw the same wave twice. I'm going to copy and paste because I can cheat. And I'm just going to do it like this so that mine match. And one more over here. So you can just see that it does repeat itself. It repeats as S curves like that. Okay, that's tangent. Okay, so now for tangent. Do we have breaks? Yeah, where do the breaks occur at? Okay. Now, if it was on 0 to 2 pi, this is tricky here. That would be pi over 2 would be the first one. The next one would be 3 pi over 2. So put over here the breaks on that are in between this interval right there would be pi over 2. And then the next pi over 2 on that interval is 3 pi over 2. If we were including the negatives, then we would include that negative pi over 2. So those are the breaks on this interval. Okay, let's talk about the domain. Is the domain all reals then? Answer no, we have those breaks. So it's all reals except for those breaks. Here's how you can write that. If you remember, what you can say is that x is all reals except for, which is the symbol does not equal, pi over 2 plus, now how far apart is every asymptote spread out? Like what's the spacing between them? Was it 2 pi's for tangent? No, it was 1 pi. So what we did is pi k. If you remember that, we did pi k. But other than this, x can be any other real number. So I'm going to do a comma. X can be all other real numbers except for these values. And k was any integer. So k-e-z, which that we're getting in writing a lot. This means that x cannot be these values, but x can be any other real number. And k is an integer, is any integer. That's what that means there. Okay, let's talk about the range now. How low does tangent travel? How high does tangent travel? While you look at the graph, I'm going to fix my colors. I wanted to do this in green so that they stand out from one another. I messed up. There we go. How low does tangent travel? How high does tangent travel? Any S curve you pick. How low does it go? How high does it go? It goes up to infinity. How low does it go? Negative infinity. So once again, you could write it as negative infinity to positive infinity, or you could say that y is any real number. Like that. Does that make sense on what we've covered so far? Now, what we're going to learn about the reciprocals is the reciprocals, what they're going to do is they're going to be 1 divided by each of these functions. So what does this mean? Now, before I go on, if you're watching the video, it's going to be hard for you, but in the classroom, look over on my wall straight across from me. I'm pointing at it says domain rules. In particular, I want you to read rule number 1. What does it say, rule number 1? You cannot divide by 0. So when we do these reciprocals, how the reciprocals work is you're going to have an asymptote anytime your graph hits the midline. Anytime your graph hits the midline, that's dividing by 0. Does that make sense? Because it's 1, these 3 functions is 1 divided by these 3 respectively. That just means in order. Like cosecant is 1 divided by sine, secant is 1 divided by cosine, cotangent is 1 divided by tangent. You will get an asymptote anytime the graph itself is at a 0. Because you'd be dividing by 0. Does that make sense? So sine, where do we hit 0? Well, we hit 0 here, here, and there. What are those values? Let's fill it in. What's the x value when I'm at 0 here? 0. What's the x value here? Pi. And then 2 pi. So we will be undefined when x is 0, pi. You don't actually have to include 2 pi because it does a parenthesis. But if you wanted to, if it helps you out to understand, at 2 pi we would have another one. So I'll do this. I'll put a bracket on there so that I can leave it. Because technically with the parenthesis I will not leave it. I'll do a bracket so that says included. So those would be those places that's undefined. So what does that mean? Would my domain be all reals? No. It would be all reals except for these values. So I'm going to use this model. We're going to say x cannot equal. You would pick one of those. I'm just going to pick the first one. Is that okay? You would pick one of those, and then you would do plus how far apart they are. What's the spacing between 0, pi, and 2 pi? How far apart are each of those? Pi. So you do apply pi k. This means x cannot equal those values, but x can be any other value. So I'll do comma x er. That means x can be any other value except for those. And once again, k is any integer. Now, what cosecant is going to look like as a graph, I'll show you in the next page. It's going to be a bunch of parabolas. And here's the way to think about it. Cosecant is going to be a parabola where sine is all the values between 1 and -1. The parabolas are going to be all the values except for anything in between -1 and 1. So the range, I'm going to have to show you in the next slide. Just write it down for now. It's going to be all reals except for, whoops, it switched colors. All values except for where the range exists there. So it'll be -1, borrowing the minimum maximum. Those they will meet at. It'll be -infinity to -1, union 1 to infinity. Right now you're just writing it down. You don't know what it looks like. I'm about to show you in the next slide. What this means is where the range wave actually is operating, cosecant will actually operate where sine does not. So sine is always between -1 and 1. Cosecant will be all values except for stuff inside of -1 to 1. I'll say it one more time. Sine operates between its range between -1 and 1. Its reciprocal will be all values except for what's in between -1 and 1. And you'll see this on the next slide. It'll make more sense. Okay, let me go to secant. Once again, secant's going to be 1 divided by cosine. So you're going to have issues anytime you hit your midline. What value am I hitting the midline at right there? Give you a hint. This is 0. That would be pi. What's this midline right there? Pi over 2. What about this midline? Okay, good. Pi over 2 and 3 pi over 2. You might notice those are the exact same values as tangents undefined. Why is that? Because tangent, by definition, tangent sine is y, cos is x, tangent is y over x. Secant is 1 over x, which means they're dividing by the same variable. That's why it's the same location, because we're dividing by the same variable. So when this x is 0, this x is 0. And thus we have the same breaks, which means its domain will be exactly the same as tangent's domain. So you can just copy that right there. X cannot be pi over 2, nor any value that's 1 pi away, or any number of pi's away. But x will be all other real values. and k is always an integer. So just basically copy what you put for domain for tangent. Secant's domain is going to follow the same rule as cosecant did with sine. Secant's going to be everything that cosine is not. So cosine is only between -1 and 1. Secant will be all values outside of -1 and 1, except for that they share -1 and 1. That's the only value they share, but other than that, secant will be everything cosine's not, and cosine will be everything that secant's not, other than -1 and 1. That's the only points they share. Finally, cotangent. Cotangent. Once again, cotangent is 1 divided by tangent, which means anytime we hit the midline here, anytime we hit the origin, we have issues. So our asymptotes are going to change. Our asymptotes are not, for cotangent, are going to be different. The asymptotes will occur when tangent is 0. So that's where those occur. What does that mean? Well, since cotangent is, wait, you tell me, sine is y, cos is x, tangent is y over x. What is cotangent's ratio? X over y. Its asymptotes are going to follow the same rule as cosecant's, because cosecant is 1 over y. Notice they share the same denominator. What does that mean? That means cotangent will have a break at 0, pi, and 2 pi. If you're like, wait, where did you get that? I got it from right here. Because cosecant and cotangent share the same y value. See that? So they'd have the same break at the same location, which means their domain would be exactly the same as well. X would not equal 0 plus pi k. Once again, x could be any other real number, and x is any integer. So I just copied that from cosecant's domain. Now cotangent, it's going to look like negative S curves, which means it's going to be just like tangent. Its domain is going to be all reals. And again, you don't know what those look like yet, but you will know within the next 3 slides. I'm going to show you pictures of all of them. All right, so there's a chart that's going to help us out like a cheat sheet when you do homework or anything else just to look at. Now, let's show you how the graphs are going to work. On the next slide, right here, it says graph y equals cosecant. Now, here's how I'm going to think about this. Okay? If everybody can follow along here, here's how I want you to think about this. When you have to graph one of those 3 new functions today, secant, cosecant, or cotangent, what I want you to start with first is figure out what is its reciprocal function, meaning the reciprocal would be y equals 1 over CSCX. Reciprocal means to flip. Now, by definition, I showed this to you earlier on, I think it was the second slide. CSC is the reciprocal of which of the 3 functions, sine, cosine, or tangent? What was it? Do y'all remember? Sine. Good. Y equals sine x. So here's how I'm going to do this. If I were you, how I graph, I think it's the easiest way. I'm going to first graph the sine function as a dotted line to help me out. Sine, where does sine begin? At its maximum, minimum, or midline? Midline. So on the origin, go to the midline. That's where sine begins. Now think of the unit circle. So we plot these points right. We're beginning on the midline, and we're thinking about the y function. When do I arrive at sine's maximum value of 1? When do I get there? What amount of pi's? Pi over 2. Okay, go to pi over 2, which would be right here. This would be pi over 2. At pi over 2, put a dot for sine's maximum. So sine's wave would go up to that maximum. Are you tracking? Okay, now, what happens when this point comes to here? Where is that in terms of y? Sine's maximum, minimum, or midline? Midline. And what amount of pi's does it take to get there? So at pi, put a dot at 0. Again, continue your sine wave like that.
With dots?
Yes, because we're actually going to graph cosecant, but this is just a model for us. So I'm graphing sine for a moment. This will make sense to you, I think, in a few seconds. Now, sine's minimum. The minimum is at -1. How many pi's is this minimum occur at? 3 pi over 2. So at 3 pi over 2, which is right here, at 3 pi over 2, put a point at -1. And again, connect your sine wave. And then finally, if we go all the way around, how many pi's did we travel to go all the way around the circle? Okay, at 2 pi, place another dot and connect your sine wave. And I'm just going to put an arrow. That right there, what I just graphed, is y equals sine x. Everybody follow? If you wanted to go fast and do the other side, you can. But I'm just going to do one period. That's how I'm going to do this. Now from here, here's how you graph the reciprocal. Am I going too fast if I continue on now? What we're going to do is we're going to add asymptotes. The asymptotes will exist anytime its reciprocal hits the x-axis, or its midline. I should say it's midline because there could be shifts, transformations. So an asymptote will exist anytime its reciprocal function hits its midline, which means I need you to add an asymptote right there, right here, and right here. Someone repeat what I just said. Why did I put those 3 asymptotes right there, there, and there? That's where sine hits its midline. Okay, now how the reciprocal works is this. When sine itself is at its maximum, that will be a local minimum for cosecant. Cosecant is going to be a parabola, and the sine maximum will represent a cosecant local minimum. It's going to look like a parabola like that. Now, sine, if I'm not going too fast, sine's local, excuse me, not sine's local, sine's minimum will become cosecant's local maximum. And this will be 1 period of cosecant right there. That is 1 period. Now you'll just repeat the process. So check this out. Remember, when we graph, I've been telling you, you need 5 key features in any 1 period. Let's count them up. How many asymptotes do you see? 3. That's 3 key features right there. You only need 2 more. What would you call this point? A local,
Maximum.
not on sine, on the cosecant graph. This would not be a maximum. This would actually be a local minimum. And then this point would be local maximum. How many total key features do we have? 5. That's enough to get you credit right there. This would be the graph y equals c of cx. And you would just repeat on this side. Okay, I don't want to take all the time to do it. But basically, how many units apart are each asymptote? Pi, or you could say 2 boxes. So you go 2 boxes over, draw another asymptote, draw another asymptote. Does that make sense what you would do? You would go 2 boxes over, asymptote, 2 boxes over, asymptote, like that. Sine, what would sine do going this way? You don't have to follow. I'm just showing you. Would it go up or down? It would go down to -1, and then it would go up to 0, and then it would go up to 1, and then finally down to 2 pi. You see how that makes sense? Once again, what do you do at sine's minimum? That becomes a maximum of cosecant. And what do you do at sine's maximum? That becomes a maximum of, no, not a maximum, I'm sorry. Sine's maximum becomes a local minimum of cosecant. Make sense on how that works? That's how we'll graph these. Okay, let's fill this in. Is the domain for cosecant all reals? No, we had breaks. Where did the breaks occur at? I'm going to say where x does not equal. Where is that first asymptote located at? 0. So x does not equal, let me do it in red since I did it in red over here. X does not equal 0. And then how often do those repeat? At every pi. Notice that's 1 pi. This is 2 pi. This would be negative pi, and so on. So you would say plus pi k, since they repeat every pi value, where once again, k is any integer. Are you tracking with how I'm doing this? Now you can see the range. Before I had to just tell you the range, now you can see it. Tell me about this piece of the range. Range means up and down. Let's do lowest first. How low does this parabola itself right here go? It goes down to negative infinity. So you would say from negative infinity, I'm going to not do this in red. I'm going to do this one in blue. Here. How low did you say negative infinity? What? Blue. Negative infinity. Okay, how high does this part of the parabola travel? -1. Now, they do share that point, so it's a bracket. They actually attain it. Now, let's talk about these other parabolas that are up here. What's the minimum of these parabolas that are facing up, that are concave up? Let me use a better word. 1. And then how high do those go? Positive infinity. Great. To do the asymptotes, it's exactly the opposite of the domain. Instead of saying x does not equal, you would say x equals. I didn't do that, -2 pi. Let me do that. So you would just say x equals 0 plus pi k. If you're wondering, do you actually have to include the 0? No, you don't. I should have done k easy. Sorry. Zero plus anything is just whatever it was adding to. Okay, finally, symmetry. Check this out. Take this point right here, this minimum. Does this minimum reflect straight across the y-axis, or does it go diagonal? Diagonal. We call that symmetry with the origin, an odd function. Okay, so symmetry, it has symmetry, it's symmetric with respect to the origin, which means this is an odd function. I'll give you a rule about that later to help you remember. But for now, just write this in. Here's what that means. If you took any one point, and for example, this point, it has an x value of pi over 2. It has a y value 1. If it's symmetric with the origin, that means if you make both the x value and the y value negative, you should hit the graph, and it does. Over here at this point, notice it has a negative pi over 2 as an x value and a -1. To have origin symmetry, it means when x changes from positive to negative, the y also changes from positive to negative. To be an even function and go across the y-axis, that means even though x becomes negative, the y stays the same value. So this one's has origin, it's symmetric with respect to origin, it's an odd function. Now let's look at secant. So how I want you to think about graphing secant. I'm going to talk through this like I did not teach the first one. I'm going to walk you through. This is how you're going to think about all three of them. When you're trying to graph secant, I want you to first think of what is secant's reciprocal. If I were to write this as 1 divided by secant, that's the reciprocal. What function is 1 divided by secant equal to? Cosine. So how I would start if I were you is I would graph a cosine. Tell me about cosine. Where does cosine begin? Its maximum. It begins at its maximum of 1. When does cosine reach its minimum value at -1? No. Think about the unit circle. It's on the far left. Cosine gets its minimum at the far left. Whoa, that was weird. This is its minimum. It's at pi. So if we start at 0 at its maximum, its minimum is at pi. So go to -1 at pi. When will it get back to its maximum? 2 pi. Go to 2 pi. Go back to the maximum. Let's connect these with the dotted dashed line to represent the cosine wave. And this will help us graph its reciprocal. Now, secant is going to have asymptotes. The way you think about it is since secant is the reciprocal of cosine, anytime cosine is 0, secant will have an asymptote. Said another way, anytime cosine hits its midline, you will have an asymptote. According to what we've drawn so far, how many asymptotes will we see here? 2. We're going to see an asymptote here and there. Go ahead and add those in on your graph. Those are the 2 asymptotes for secant. This is x equals pi over 2. This is x equals 3 pi over 2. Are you tracking with me? if you wanted to repeat the process, how many blocks apart are each asymptote? 2. I'm going to add one more just for my drawing, and then I'm going to stop. I'm just going to write the word repeat over here when I get there. This would be at x equals negative pi over 2. Okay, I have put on how many key features now? 1, 2, 3. This would not be a key feature of the graph. That's actually cosine's graph. So I have 3 so far. How many do you need for delta math? 5. You would need 2 more. What you do is just like secant has the same relationship to cosine as cosecant did to sine, which means what will a maximum become, a cosine maximum become for secant? A local minimum. Draw a parabola that goes up and follows your asymptotes here and here. I didn't put here y equals cos x. Okay, and now what will this cosine minimum become in regards to secant's function? A local maximum. Once you plot those 2 points on delta math, you would have 5 key features and finish in the rest. I'm going to go ahead and put this one on just since I have it on the graph. I'm just going to put that on there. And then I'm going to write the word repeat over here. Everybody follow along how we're going to do that? So the graph, all the reciprocals, you're going to do the reciprocal function, which means cosecant, secant, and cotangent. You're really going to think about sine, cosine, tangent to accomplish the task. All right, let's talk about domain. Is the domain for secant going to be all reals? No, we have breaks. Those breaks are in red, so I'm going to write the domain in red. Where does the breaks occur? Where do the breaks occur? At pi over 2s. They occur at pi over 2. So what I'm going to do is just write down the very first one. We're going to say x cannot be pi over 2 plus. Now, how far apart are each of those spread out? Let's think of it this way. Pi over 2 is here. 3 pi over 2 is here. That's half a circle. How much is half a circle in terms of radiuses? It's pi. So it'd be pi k apart. So the domain x could be any other reals, but k has to be an integer. K is any integer. But those are the spots where the domain will not exist. The asymptotes will be at these spots where there's breaks. So if you want to go ahead and fill that in asymptotes, the only thing different is you use an equal sign. X will equal pi over 2 plus pi k. It's only those values, you don't go in between, so you don't do x all reals, it's just those. But you would say the k easy. K is any integer. Okay, let's talk about the range. Take a look at the graph. Looking at the range, that means up and down. How low does this parabola, I'm going to look at the bottom parabola. How low does this bottom parabola go?
Negative.
Negative infinity, very good. How high does this parabola get? A maximum of -1, a local maximum, I should say. Union. Now let's talk about these parabolas that are concave up. What's the minimum on these concave up parabolas? 1. And what are their maximums? Perfect. Great job. Okay, now for symmetry, what you would do is you would take any x value and you'd compare it to any other x value that's straight across. Sorry, that's opposite. So for example, let's take this point right there. The location of that point is pi to the right and it's down 1. If I went pi to the left, that means negative pi. Would my point be at positive 1 or would it be at -1? If you kept these, it would be -1. Wouldn't it be like this? You see how it'd be like going like this? Whoops. Since it would go down this way, I have a question for you. When you plot that point, did my x or my y value stay the same, or did my x or y values change? That means it's an even symmetric with the y-axis. It's symmetric with the y-axis. Symmetric with respect to the y-axis. And if it's symmetric with regard to the y-axis, that means it's an even function. When you compare the points to be an even function, that means negative x comma y is going to correspond to positive x y. That whether x is positive or negative, you get the same y value either way. That's what it means to be even. I didn't write that down on the odd function. I should have. Here, what it means to be odd is that if you look at a negative x and you have some y value, that will correspond to a positive x where the y changes like that. So y changes when x changes. That's how what odd functions are. That's the definition of odd. Even is like that. Okay, we have one more to look at. What's our last one to look at? Cotangent. Let's take a look at cotangent. We'll try to go a little quicker here as best I can. First, it says reciprocal. And what I want you to think of is if you took the reciprocal of cotangent, it would look like this. 1 divided by cotangent. What is 1 divided by cotangent equal to? It is x of y. Sorry, what trig function? Tangent. Cotangent's reciprocal is tangent. So what I want us to think about is graphing the tangent function here. Tangent, if you remember, had asymptotes. Do you remember where the asymptotes occurred? It was pi over 2's. And so tangent looked like this. For one period, it was an S curve that came through the origin and went up to pi over 2 like this. This is what cotangent looked like. No, I'm sorry. That's what tangent looked like right there. That was y equals tangent x. And it just repeated. From pi over 2, it's going out of order. From negative pi over 2 to pi over 2, it would look like that. It would just repeat. That's tangent. Okay, that's what tangent looked like. S curve between negative pi over 2, pi over 2. That was tangent. So when we talk about cotangent, it follows the same rules. You would say first, what do I mean by rules? Anywhere tangent equals 0, cotangent's going to have problems. How many times does this graph, way I've graphed it, how many times does it hit the x-axis or its midline? 1. That's going to become the new asymptote. So the asymptote is now going to be here. Are you tracking? That's going to be the asymptote. That asymptote would be at x equals 0. Now tangent had asymptotes at negative pi over 2 and pi over 2. And the reason was tangent is y over x. At your pi over 2's, that's where x is 0. At pi over 2 and 3 pi over 2, that's where your x was 0. That's why tangent wrote there. Cotangent, though, is x over y. So we're looking at when y is 0. Well, y is 0 at 0, pi, and 2 pi. So that's where our asymptotes will be. They'll be located at 0, pi, and 2 pi. Because that's where y is 0 on the unit circle. Now, so how many key features do I have right there? 3. If you were on Delta Math, you would only need 2 other points. 2 other key features. Cotangent is going to be just like tangent, except for instead of it being an increasing S-curve, it's going to be a decreasing S-curve. Remember, you go off the D value. This doesn't have a D value. You put your point of inflection in between your asymptotes like that. That's all you would need on Delta Math. It would fill in the S-curves now. You put on those points of inflection. But cotangent is going to be a decreasing S-curve. So it comes in like this, and then it decreases down. Those are pretty ugly, but they'll satisfy. And you would just repeat the process on this side. That would be cotangent. Whoops. All right, let's fill out. Looking at the graph, is the domain all reals?
No.
No, absolutely not. We have breaks. Where do the breaks occur? Where's the very first break occur? At x equals 0. So we would not equal 0. Nor any value. How far apart does each break come? Pi. Every pi apart. So you put plus pi k. Now, the domain could be any other x value, which means all reals except for those. And once again, k is always an integer. Anytime we write a letter k, we're going to put kez. K is any other integer. So that just means we'll have a break at every whole number of pi or negative whole number of pi. That's what an integer means. Okay, talk to me about the range. How low does any S curve go? Negative infinity. How high do they go? Okay, so we're going to go from negative infinity to positive infinity, which you could write that way, or since we're talking about y variables, you could say y is any real number. Okay, asymptotes. This is just like domain, except what do you do different? You don't say does not equal, you now say equals. And you actually do not include the XER because X is not the values in between on asymptotes. It's only those values. So you wouldn't say it's all other reals, but you would say K is still an integer. Symmetry. It'd probably help if I drew another one. If you thought about one real quick, I'm going to erase this in a second because it's going to look ugly. But if I drew another S curve through there, does it appear to, if you take any point, does the point go straight across the x-axis? Or does it go diagonal? Diagonal. So I'm going to erase that part. We would say if it's diagonal, it has symmetry across the origin, which means yes, it is an odd function. So the cheat to know if it's an odd function or an even function. If the function's ratio has the letter y, it's always odd. So again, if the function has a ratio with the letter y, it's odd. Okay? Oh, you don't have to repeat it to me. I'm just letting you know. If you think about the ratio, what is cotangent's ratio? Sine is y, cos is x, tangent is y over x. What's cotangent? X over y. If it has the letter y, it's going to be origin odd function. The y's will switch positive, negative. If it doesn't have a y, that's when it's even. Okay, so if there's no y, then the y's will be the same on both sides. If it does have a y, the y, when you're on the left side of the graph, the negative side of the graph, the y will switch signs as well. Okay, and I think that's it. It's time for our first DOL. Let's go to DOL. Well, our first DOL, call it DOL number 3. Let's go try that in the back of the packet. DOL number 3.